Hi, and welcome to today's webinar about 7 reasons not to put an external cache in front of your database. I'm Eric Koslow. I'm an editor for InfoQ. I have a main focus on Java and application security, and I'm interested in hosting and attending this webinar because my team uses a decent amount of caching, and I've had to deal with this problem recently. I know a lot of us have been taught and experienced the idea of kind of sprinkling caches around, putting them in front of databases, having certain paths and use cases go around them, ensuring our cache validation happens, and just about everything else. And while caches can be fast and accurate with the right invalidation strategy, ScyllaDB has found a way to make them faster and more accurate by putting them inside the database and closer to that data. So if you're a developer or architect who deals with latency, or you're a new architect who looks at someone else's design and just sees caches kind of tossed in like sprinkles, we're pretty glad that you're here. Today, we're going to hear from 2 experts. Tomasz is a distinguished engineer from ScyllaDB who's implemented caching in Scylla. In particular, Tomasz has spent a good amount of time measuring the problem in a way that can really improve your applications. And Zach is the VP of product for ScyllaDB, who can help you show the impact of using this caching style to your stakeholders and managers so that you can fully explain the benefit. And if you have any questions, ask away. There's a questions section over on the right in your chat there. And I'll be monitoring them during the webinar so that we can ask them live at the very end. If you have a question, chances are someone else wonders about it too, so don't hesitate to ask. Just type it into the chat or send it directly to me. Otherwise, yes, the slides will be available after the webinar, so you'll get those in advance. Now, Tomasz and Zach, over to you.
Thanks, Eric. So you already introduced us, so I won't introduce us again. As you noticed, I'm actually much older than my picture, but Tomasz looked pretty much the same. So I don't know why, but that's how it is. A quick poll before we get started. Are you actually using right now a cache in front of your DB? Let me see. I'm trying to see the result of the cache. You can also raise your hand if you're using a cache in front of the database. Okay, I cannot actually see you because you don't have a camera, and maybe we'll share the result later. So before I jump to the actual topic, a quick introduction to Scylla, the company, and Scylla, the project or the product. So ScyllaDB is a NoSQL database which is compatible with both Apache Cassandra and Amazon DynamoDB. It has actually two distinct API supported. Scylla was designed from scratch with performance in mind. And when I say performance, I mean both high throughput and, more relevant to this session, low latency, in particular tail latency or P99 latency. Scylla have 3 main variants. The first one is a cloud offering, and we're certainly not unique in that. All the vendors have a cloud offering these days, and we are no different. So a DBAS or a SaaS offering of the database running on AWS and GCP. The second is an enterprise version, a closed source project, which you can download and run either on-prem or on the cloud. Actually, most of the enterprise users are also running on AWS and GCP and Azure, but I guess they want to control the database on their own. And last but not least, an open source project. You can go to GitHub, download the code, compile it if you have an hour at least, and run it yourself for free, and we will do our best to support you as a community user. Some of our customers and users are mentioned here. I won't spend too much time on it, but after Tomasz's section, I will actually go back to a few of the names that you are seeing here and explain a little bit about their topology and how some of them drop the cache in favor of just using the database directly. Okay, so what are we going to see today? So I already did the ScyllaDB intro. Next, I'm going to explain why latency is critical. Don't worry, I won't spend too much time on it. I think it's a pretty common knowledge these days. Second or third, I will explain why placing a cache in front of the database might not be a good idea. So I'm not, full disclaimer, in some cases it might be a good idea to put a cache, but in some cases it's not. And in this session, I'm going to focus on the not part. Then I'm going to switch to Tomasz, who's going to explain Scylla caching design. Scylla also have an internal cache inside it, and we'll try to convince you why it's better to use this cache instead of an external cache. And last, we're going to do a quick summary, mention a few customer use cases in this scope, and do a Q&A. So why latency is critical? I think it's like a common knowledge in the industry these days that latency can be translated to revenue pretty fast. If you are using an application or a game or whatever, and you get in bad latency, it immediately affects your user experience, and there is a higher bounce rate from your website or from your e-commerce site.
Just a second, do you mind dropping the screen share and sharing the screen again? Because it appears that the quick poll is up, and I was not able to remove it through my controls.
Sorry, okay, I don't see it on my side, but okay, so let me do that.
Yep, drop the share and then share again.
Okay, how do I, give me a second, I'm trying.
There we go. So there's those wonderful slides that you'll all get at the end.
Okay, I'm not sure what I did, but if it's worked, great. Okay, one more thing I want to mention about latency that some people don't realize. In Scylla, at least, we're focusing a lot on the tail latency and P99 latency, and some people think that it might not be as critical for their application because it's just 1% of their requests. So, okay, 1 out of 100 customers get a bad user experience. Maybe I can live with that. But the reality is that even the P99 latency can affect your entire system. And there are a few reasons for that. And one reason that a mobile application or a web application or a game or whatever actually can send a lot of API calls to your business logic layer, which can be translated to 100 or 1,000 requests to the database. So even if just one of these requests having a slow response, depending on your application logic, it might slow down the entire application. That's one reason. The second reason is what Gil Tenne called coordinated omission, meaning that every application have a limited number of threads or processes running. So if the database slow or the cache slow down one request, even if it's just 1 of 100, all the requests that come after it actually slow down as well. So P99 latency might be critical. When we design Scylla, we try to optimize the P99 latency, and maybe Tomek will talk on that a little bit later. If that topic interests you and you really want to deep dive into technical aspect of P99 latency, there is actually a full conference about that. Scylla is one of the main contributors to this conference, and you are welcome to take a look at the P99 course. Okay, so by now you're convinced that latency is critical, and you are thinking to yourself, okay, my database is pretty slow, maybe I need to put a cache in front of it. So in the next 10 minutes or so, I will try to convince you it's not always a good idea. So first of all, why would you put a cache in front of your database? So the quick answer is improve latency. Let's say that this person here is your application, and you are trying to either write or read from the database, but the database is on a remote location. It takes 50 milliseconds just to get to the database over the network. The database is pretty slow as well, so it's taking him 50 milliseconds to process. Altogether, you can already get 150 milliseconds round trip plus database latency. Of course, it's not acceptable for many real-time applications. So you are thinking to yourself, okay, I know how to solve it. I will put a cache in front of it. So the application will first go to an external cache. With some luck, I get a response back in less than a millisecond. If it fails, I can always fall back to the database with the terrible latency that I got before. So that's the motivation of putting a cache. This is why a lot of people do use this mechanism. And in some cases, it does justify itself. There is a hidden assumption here that there is a hot subset of the data that will fit into the cache, because the cache is usually memory-based. The data is sitting in the RAM, it can be Redis, Memcache, whatever. If it's not the case and the data is evenly distributed, the cache won't be as useful. But in most cases, it's a fair assumption that the data is not evenly distributed, and such a cache can bring benefits. And next, I will cover 4 types of cache people use, and I will try to explain which is better or worse in which case. And of course, it's all about trade-offs. So the first type of caching is a cache that I'm sure you all seen, which is embedded in the application itself, either in the memory of the process or a process near it on the same server. This is one type of cache. The second type of cache, which is pretty sophisticated, is an external, what I call external transparent caching. One good example of such caching is that if you're using DynamoDB comes with a cache called DAX, which is completely transparent in a sense that it doesn't have a different API. It uses the same API as DynamoDB. It does come with some extra complexity. I will talk about it a little bit later. A third type of cache, which I'll focus on my section, will be external cache, which is not transparent. For example, and this is something that we are seeing a lot, you have Redis for your caching, and if it fails as a cache, you move to Cassandra or other database as the source of truth or main data store. And the last type of cache that we actually going to cover, Tomek is going to cover later, it's a cache that's embedded in your database. Most databases, or I dare to say all databases, have some kind of internal cache inside them, implemented in a different way. Some use mmap, some use other methods, but I will leave this part for Tomek. So we cover type of database, and now I want to convince you why in many cases this caching is not actually required. So first of all, let's address the network latency. When you deploy on the cloud, and most people deploy in the cloud these days, if you are deploying your application and database in the same region or even in the same zone, it's typical to get less than a millisecond latency to the database. So the reasoning of the round trip become irrelevant, at least in this case. Second reasoning is slow response of the database. I already mentioned that ScyllaDB was designed from scratch for performance and low latency. And in most cases, it will get an average latency from ScyllaDB of less than 1 millisecond. Even the P99 usually less than 5 milliseconds. So if you don't have the network latency, you don't have the database latency, the reasoning for a cache becomes less obvious, and in many cases, you don't actually need it. So I try to explain why you might not need a caching, but now I want to trash the cache even further, if you will, and try to explain why the cache can actually hurt you. And this is something that people might not realize in first glance. So first, the cache actually might introduce additional latency. So if you are running in the same zone like the database and you get good latency from the database, adding another hop, especially if you go first to the cache and then to the database, even if it's not Cassandra, even if it's Scylla here, you still have another hop in the network, another processing. So actually you are trying to save latency, but you are adding latency. So that's one reason that an external cache might hurt you. Second reason, which is pretty straightforward, it's another component, it's add complexity and it's add cost. And this is true, by the way, not just for a combination of Redis with Elastic or with Cassandra or whatever, also true for transparent external database like DAX, which I mentioned earlier. Even in the DynamoDB case, the DAX run on extra machine, which have extra cost and need sizing and such, so you're adding both cost and complexity. Third reason, which is a little bit tricky sometimes to understand, cache decrease your availability. So if you're working with a symmetric distributed database like ScyllaDB, and there are many other examples, the database is evenly shared between many nodes and many cores. And if one of the nodes fail, other replica on the database give you a similar latency and similar availability. If you use external cache, you don't have the same experience. some of the external cache is not highly available on its own. So if you have a failure of the cache, you still have availability in a sense that you can go to the database and get the information from there, but suddenly you got a huge latency spike. And why is that? If you use cache, you are basically cheating or confusing the cache that the database itself holds, as the database, as the cache of the database or database itself become cold. So yes, you will get a response back, but still any database will not use its internal caching and you will get cold data. More than that, still I have a mechanism called heat-based load balancing. It's a cool feature that allows Scylla to choose between the replica, the one which is most hot, in a sense that the cache there is hot. So if you have a failure of one node and this node coming up and starts serving requests again, Scylla will make sure not to send requests there until the cache there become hot and it can serve requests with low latency. So availability in this case doesn't mean that you lose information, but it does mean that you have latency spike if you use external caching and you have a failure. Another reason, which is pretty straightforward, is additional complexity. Just holding two sources of information, one database and one the caching, and trying to synchronize between them is not trivial. There is a known saying in computer science that caching validation is one of the hardest things to do. I will leave you with the second one. I won't mention it here. But it's not trivial to manage these two. Even if the database returns like a nil result or the database, the value is not there, you might want to go to the cache and update the cache as well. So the interaction between these two information sources is not as trivial. And this complexity basically moves to the application and the application developer. Okay, now we move to the reasoning, which is, I think, is the most important one and least obvious one. The database holds a lot of information about the data, and there are two types of information I want to split this information into types. One type is the schema or data modeling, and the other type that I will cover in the next slide, I guess, is workflow information. If you use, for example, think of an example that you use either Oracle DB or Scylla or MySQL or what's not as a database, and Redis or Memcache as your caching. These two database and cache have completely different schema, completely different properties, and they does not match each other in many aspects. For example, Scylla is a key value or wide column database. Your caching, if you use Redis, is key value. Still have a definition of table, user-defined types, and many other aspects. Redis have a complex structure of its own, but it doesn't match each other. So if, for example, you define a table in Scylla, the table itself, the notion of the metadata of the table does not exist in the cache, so the cache cannot optimize for that. Spoiler alert, Scylla can optimize for that because it's an internal cache and can serve information better. Scylla also have properties like caching per table. You can define the specific table as a table that you don't want to cache or do want to cache. This information does not propagate to the caching layer. The application, if it's smart enough, can propagate or can take care of this information, but it's not trivial. Time to live is a property of many databases like Scylla. If you define a time to live on an information element in Scylla, once this element expires and deleted from the database, the cache doesn't know about it. So it's not, now you need to both synchronize the cache and the database, which I already mentioned, it's not trivial, but also you are just wasting the cache, which is pretty expensive, with data that was already expired. And there is another property of the database which are not propagate to the caching. So this is like for people who are not familiar with Scylla, what is the difference between a key value and a key value? So this is how a key value like Redis or Memcache will look like. And this is how, it's a very high level, but this is how a key value or a wide partition database would look like. There are partitions and there are many rows inside the partition. Another property that I mentioned earlier, caching setting in the database itself. In Scylla, you can specify if you want to enable or disable the cache per table. You cannot do that in the cache layer. Or you can do it, but it's complex. I already mentioned time to live, so I will move forward. Another type of information that is missing from the cache and existing on the database is workload level information. Workload prioritization, I will explain what it is in a second. In Scylla, when you do a request to the database, you can specify that this request should be cache or shouldn't be cache. Similar to what I mentioned on the table, but on the request scope. So for example, if I'm doing a full scan of a table, usually I don't want to cache this information. So I can let the database know that this doesn't need to be cache, but it's harder to do on the cache side. Another not obvious problem with the caching layer is completely ignoring the security or role-based access control that I have on the database. So usually on the database, I'm taking the time to strictly define which table can be accessed by which user and which role. A table can be read only to one user, write only to another user. All of this information completely missing from the cache. So if someone has access to the cache, it can basically read information from all tables, from all users, and basically you lose all sense of security or role-based access control this way. So something to think about when you design a system. This is just a quick CQL. CQL, by the way, is the query language of Apache Cassandra and Scylla. This is an example how, as I mentioned earlier, I can control in the session level if I want this query to be cache or not. I want to deep dive into the syntax because it's not the focus of this session, but if you are interested, I welcome you to go to Scylla documentation. Workload prioritization, it's a cool feature that maybe I will spend a minute on it just because it's cool. In many use cases, you're actually running two different workloads for the database. One is the real-time OLTP workload, and one is an analytic workload. This workload has completely different latency requirements. Usually the real-time require low latency, the analytic not as much. And Scylla have properties that allow you to define which latency do you want to get from each kind of workload. This is an example, another example of information that the database actually holds, but the cache is completely ignorant of. So when you're using the cache layer, it's completely missing this meta information the database has. And by that, I hope I convinced you that putting an external cache in front of Scylla might be problematic. Next, I will switch to Tomasz, who will try to convince you why Scylla caching is more useful. Okay. And now I make Tomasz the presenter. Or did I?
Okay, thank you, Zach. Hi, everyone. So I will tell you a bit about some details of how cache is implemented in Scylla. So cache in Scylla lives on the replica side. So let's start by examining how the data flow looks like on the replica side. When we have a write, which arrives at the replica, it first blends in a data structure which is called a mem table, which lives in memory, in RAM. And of course, we also write it to the commit log for crash recovery, but this part is not relevant for today's talk. And when the mem table is large enough, we flash it to disk into a data structure, which is called an SS table, which is an immutable data structure, and which forms log structure merge tree. And after that, the mem table is removed from the memory. So when we have a read, the read has to combine data from both the mem tables and the SS tables on disk to have a consistent view on the data, which includes all the writes which were previously written to the database. And for reads, the consistency is quite easy to achieve in this scheme. It can be, for example, achieved by taking a snapshot of mem tables, pinning them in memory, taking a snapshot of SS tables, and then combining the data from all the sources. But in this case, we are missing the cache, so such a read is very slow because it has to go to disk every time and read from multiple files. So what we want is to have a cache which protects the read from going to disk every time. And such a cache would be a read-through cache, which semantically represents everything which is on disk in OSS tables, and caches a subset of data which is in SS tables in memory. So a traditional way to implement that would be to use a buffer cache, which is basically about caching buffers which we read from those SS table files in memory. Those buffers are 4 kilobytes in size typically, and that's what you would get, for example, if you use the Linux page cache. But there are some problems with this approach, and we don't use it. One of the problems is that it leads to inefficient use of memory, because to cache a single row, you need to cache a whole buffer in memory, and the buffer is 4 kilobytes, and the row can be much, much smaller, for example, 300 bytes. And if your data set is larger than RAM, then access locality is not very likely, and you have inefficient use of memory. And even more so, it affects negative caching very poorly, because cache the fact that you don't have a key, you have to also cache the whole buffer. So efficiency is even lower. Another source for inefficiency in this approach is that since the read needs to possibly touch multiple SS tables to fetch the row, we would have to cache multiple buffers in order to cache a single row, which leads to inefficient use of memory. And the same thing also impacts CPU overhead. If we have to touch multiple buffers every time we read, we have to spend CPU time on merging data from those buffers. And another source of CPU overhead in this case is that if we store buffers, then we need to parse those buffers. And SS table format is not optimized for read speed, it's optimized for compact storage. For example, in the format we inherited from Cassandra, you have to parse index buffers sequentially in order to interpret the index. Then you have to parse the data file, which also costs some CPU. Another problem is that we can get premature eviction, which we don't want due to SS table compaction. SS table compaction is a process which rewrites SS tables because they may contain redundant or expired data. So the process basically writes a new SS table and deletes the old files. And when it deletes the old files, it implies that the buffers have to be invalidated, which sort of invalidates the cache, and read performance suffers as a result because the reads will miss in the cache. So this is not how our cache works. We don't use a buffer cache. We use an object cache, which is similar in structure as the mem table, and doesn't suffer from the problems which I mentioned. It's optimized for low CPU overhead. We have a single version of a row which combines data from all relevant SS tables, and the caching is done with row granularity. We also don't use the Linux page cache at all. Most of the memory which is available on the node is reserved by Scylla. We only leave a very small reserve for the OS for stuff like socket buffers and other data structures which kernel may need. but most of the memory is managed by us, and we dedicate most of it to the cache, which is designed to fill all available memory and shrinks on demand as there is pressure from other parts of the system, like mem tables or things which are needed to handle ongoing operations. And there are controllers in place which make sure that those other parts and mem tables don't grow too much. So most of the memory will be dedicated to cache. Another important piece of design which we have has to do with sharding. Every CPU in Scylla is responsible for a subset of data, and every CPU has separate data structures to manage that data. So every CPU has separate cache and separate mem tables. And those data structures can be accessed only from that CPU which owns them. And another important piece to that is that we have a thread per core architecture, which means that all processing is done in a single thread per CPU. And execution is divided into short tasks which are executed sequentially with cooperative preemption, which means that we can control in code exactly what are the boundaries of the tasks. And what this allows us is that we can have complex operations on data within the task without having to deal with real concurrency, which you would get if you use multi-threading and access data from multiple CPUs. So we don't have to use logs, we don't have log contention because of that, and we don't have to implement complex log-free algorithms. Our data structures and algorithms can be simple. So for example, when you have a read, it can access cache and mem table, look up in them in a single task, and have a consistent view on both as if it worked with a snapshot. And that can be achieved without involving any synchronization mechanisms. So everything works fast and has a very predictable performance. There is some challenge related to object cache, and that has to do with supporting our query language and the data model. Scylla is not a simple key value store. We have to support more complex operations, like, for example, range queries and range deletions. And that impacts how caching is implemented. Those problems are not present with the buffer cache, but are present with the object cache. Take range queries, for example. You have a query which wants to scan a set of rows. And if you had a cache which is just key value, then you wouldn't be able to use such a cache to speed up the read, because you don't know if between the entries which are in the cache, there isn't some data which is stored on disk in SS tables. So such a read would have to always go to disk for the gaps. And our cache is designed to handle this case. We store information about range continuity, which means that a given range in cache is complete, and the read doesn't have to check the disk if it contains anything. So if you repeat a scan, it will not go to disk. Also, range deletions require special handling due to eventual consistency model. Deletion is not just about removing data. It leaves a marker for future reconciliation, and this marker is called a tombstone. And the cache needs to be able to store this marker. And our cache is prepared to handle that and piggybacks on the range continuity, which I mentioned earlier, basically annotating the range continuity information with the tombstone. So the key takeaways from this are that ScyllaDB has a fast cache, And the cache access and maintenance is efficient due to our design and due to collocation with the replica. And our cache takes care of upholding all the semantics of the query language and the data model, and also the consistency guarantees, which could be problematic for an implementation of external cache. Okay, now back to Zach.
Thanks, Tomasz. Now let's try to switch the control, which is technically challenging more than writing a database. Okay, I think we did it. Great. So thanks. I hope you guys are convinced that writing a cache, an efficient cache, is not trivial, actually quite complex, but the advantage of writing it in a database that it can use the information a database has. Before we finish, I quickly want to show a few for customer use cases that actually got rid of the cache layer and moved to using Scylla directly. So a few of the companies that actually make this information public, so I'm not sharing any secret here. They talked about it in the past. One such customer is Comcast, which I'm sure many of you know. Comcast moved from quite a large Cassandra cluster deployment to a smaller Scylla deployment. They were able to do so because the throughput in Scylla is better. They also been able to drop the cache layer that they had in front of the database because the latency is much better with Scylla. And I think Tomek gave you a few insights of how we can get to such latency. It's actually only part of it because Tomek focused on the latency and performance of the caching element, but we have a lot of work of how we optimize the storage access. But maybe that's a topic for a full-blown session at another time. Other customers that prefer not to share his name, also with streaming services, was able to get rid of both a combination of Redis and Elasticsearch and move to Scylla. Again, it's a common pattern with our customers. Once they move to Scylla, they are able to drop the cache, and in the process, they benefit from a lot of the value that I mentioned earlier of removing the cache. And just to show that not all of our customers are video streaming or media companies, although we have many of those. Grab is a popular delivery company in SGR. I think if for those of you from the US, maybe similar to Uber Food or delivery or something like that. They, again, another use case of be able to move from Redis to ScyllaDB without losing latency and gain, of course, durable storage and high availability, and other cool property of NoSQL database. More example of such customer, you will be able to look through it in the slide. We will share it later, so I don't want to spend too much time on it right now, and jump to the summary and the Q&A. So recap what we've shown today. I try to convince you on my part that putting a cache in front of your database might be a bad idea. Again, in some cases, it might be a good idea, but it's in particular in the cloud, and if your database is fast enough, it might actually hurt your latency and complex your entire system. In this section, Tomek tried to show why the internal cache in Scylla is actually doing a better job than external cache, mostly because it was optimized to work with Scylla and with Scylla information. And in the last part, I quickly go over a few of our customers, proving to you, I hope, that removing the cache layer is not something theoretical. It's something that many customers and many big production systems are actually doing. And with that, I want to thank you and move to the Q&A part. And I will be more than happy to hear your question. You can write them down.
Sounds good. Thank you very much for the presentation. And just for everybody else, there's a questions section in the meeting. Otherwise, you can shoot them directly to me. Just figure out how to use the chat and we'll get all of the information to address any questions that you maybe saved until the end. All right, so in terms of sizing, one of the questions people asked is, can I just store all of the data in the cache? And why is the cache more limited in space than just the database itself?
Yeah, obviously you can't, otherwise you wouldn't need a database. So the way that most caches work, and maybe Tomek can later expand on how Scylla implement the cache, but the way that most caches work is putting the information in the RAM of the machine and not in the storage. Even with SSD, fast SSD today, access to memory is still faster than access to the storage. So if the cache is limited only to the RAM, of course, the size of the RAM is much smaller than the size of the storage, and in particular, it's much more expensive. So if you want to put, today, both the storage and RAM become cheaper and cheaper, but if you want to keep a terabyte in the RAM, you might be able to, but 10 terabyte, 100 terabyte, or 100 petabyte, of course, will be super expensive to put in the RAM. So at some point, usually after a terabyte or something like that, for the entire cluster, you have to switch to store information on a storage, on an SSD, or even spinning disk, and this is where the cache will not be big enough. I hope it makes sense.
Works for me. Yeah, if you put everything in the cache, then why have a database? All right, so just some terminology questions. In terms of the measurements that you used, you had P99. So the question was, what is P99? And I'm just going to say, what is P95 in addition to that?
Okay, yeah, we use it so often that I forgot maybe to define it. So when you're talking about P99, at least in the scope of what we are doing, you are referring to the 1% of the worst latency query. So if, for example, your average latency with Scylla is usually under 1 millisecond, your P99, the worst 1% of the query might take up to 5 milliseconds. As I explained earlier, the P99 affects the system much more than 1% because it can slow down the entire queue, it can slow down your application. So in most production system, I would say most serious production system, they look at the P99 and not just at the average.
Cool. Next question is, what's the difference between an external cache and a transparent external cache?
Okay, good question, because I haven't spent time at all about the transparent cache that I mentioned earlier. First of all, I want to say this is terms that I'm using. I'm not sure it's an industry-wide term, so don't look it up. What I call a transparent cache, like DEX for DynamoDB is a good example, is when the cache and the database have the same API. So we're actually using the same API to work with the cache and with the database. You don't have to change the API. It's not the case, for example, if your database is Oracle and your caching is Redis, or if your database is Cassandra, your caching is Memcache or what's not. You need to use two different API and it makes everything a little bit more complex. So a transparent cache is easier to use in that sense. It still suffers from many of the problems that I mentioned earlier, but at least you can use the same API. It also, in some cases, take away the complexity of validation and invalidation of the cache for you. So it will automate it for you and avoid some of the complexity problems that I mentioned earlier.
All right, so a next question that comes in here says, can you talk about a scenario where an external cache is good?
Sure, it is good in many cases. I don't want to say you should never use the cache. I would say the most typical use case is when your network latency is not as good. So for example, if from some reason your application is in one region and your database is in another region, so first of all, I will check if I want to keep this deployment because it doesn't sound great, but it might be the case. And then you want to have a local cache that you can query very fast. At least on the cloud, it's not as often as it used to be because it's very easy to just spawn a data center or a node of Scylla or other distributed database on your region. So you don't have to go to another region, but on some cases of the cloud, it might be more useful.
All right. And one question here comes in about technologies. Other databases use mmap for caching. So why does ScyllaDB not use mmap?
I think I can take this one. So mmap is a big no-no for us and for several reasons. One reason is the same as for the Linux page cache, which is that mmap uses page cache under the hood. So all the problems with the buffer cache are also the problems which the mmap solution will have. But there are more serious problems for us related to mmap, and that has to do with our architecture. We have this thread per core architecture, and if we access an mmap file from the CPU thread, then we could get unpredictable pauses of execution because the thread would page fault and had to wait for the data to be read from disk before execution is yielded for something else. So basically the CPU would be idle until the read is finished, and performance will be pretty much none. So we can't use it because of that. And even if we delegated this to a thread pool so that access is done by a thread pool, then you would suffer from performance issues related to SMP, which have to do with a kernel page shutdown, because when page faults happen, the kernel has to update the mapping and has to issue TLB shutdowns. And in SMP environment, that has a big overhead. So that's another reason. And we cannot use a thread pool because then all the benefits from our design would go down the drain. And also, yeah, there's another problem which has to do with scheduling. If we would use mmap, then we wouldn't be able to schedule IOs on our own, and we really want to, because we need to separate workloads. For example, separate read workloads from commit log writes, and because of that, we have this scheduler which collects all the current requests which go to the disk and decides which requests should go when. This way, commit log, for example, writes can jump in front of the reads, and the writes can have low latency. So if we used mmap, then all the scheduling would be done by the operating system, and we would lose control over that. So yeah, there are many reasons why we don't use mmap.
All right. Another one here is, what is the difference between two things that you mentioned, which is a mem table and cache?
Well, the difference is that mem table is a buffer for writes. It's not yet associated with SS tables. It gets flashed to disk, whereas cache is not flashed to disk. In terms of the structure, they are very similar. They are almost identical with some minor differences. And the differences have to do with the fact that cache, for example, needs to support eviction, and memtable doesn't. So the data structure in cache has to be prepared to handle eviction. It also has to be prepared to store the information about continuity. Cache may have gaps, and when a read hits this gap, then it has to go to disk. That's not the case for the mem tables, which are always read in full, which impacts mostly algorithms. The data structure is mostly the same, but algorithms need to take this into account. And the read from cache is much more complicated than from mem tables because of that.
All right, and during the poll, the answer was almost everyone said, are you using a cache in front? And they said only for a small subset of latency sensitive operations. So do you want to talk a little bit about what are effective techniques for figuring out when your caching is in the right place or where you maybe need more of it?
So I can answer in the scope of the external cache that I mentioned, and maybe Tomek can later speak about the internal cache in Scylla. So actually for both, you need good monitoring system and good metrics. And the basic metric that you want to look at is the hit rate of the cache. And if you have low hit rate, your cache is basically wasting time. If you have high hit rate, it still doesn't mean you need a cache, but at least it's a good sign that it's doing some work. If you use both Scylla with external cache, which in most cases I wouldn't recommend, you can look at the hit rate on both and try to evaluate if you need it. It's very much workload dependent. So my recommendation is to actually try to benchmark this workload with a cache and without a cache and see if you get any benefit. There is no one rule for everything, because with one database you might need a cache, with another database you might not need a cache. With one network latency you might need a cache, another network latency you don't need a cache. So very much use case dependent, and benchmarking is the key.
Okay, but an effective strategy that you indicated is put a cache in front of some of your use cases and watch the hit rate of that cache to see if it's effective or worthwhile.
Yes, but it's not enough, because even if the hit rate is high, it doesn't mean that you actually need a cache. It might be the case that the hit rate is high on the external cache, but if you remove it, your latency actually improves, because the hit rate on the database itself gets higher. So it very much depends on the use case, and benchmarking is unfortunately, I know benchmarking is not trivial, but benchmarking is the only reason.
Sounds good. All right. So there's a question here that says, so are newer caching implementations such as Cassandra and embedded ScyllaDB cache durable?
I'm not aware about the cache implementation in Cassandra, at least the recent one, but the cache in Scylla is not durable. Basically, when you restart the cluster, the cache would have to be repopulated from SS tables.
Yeah, well, one thing I want to mention, the cache itself is not durable, but of course the data is durable. That's one thing I want to mention. The second thing is the feature that I mentioned earlier, which is the hit-weighted load balancing, which is a feature we developed in particular to mitigate this issue that if you have a node restart, it's starting with a cold cache. So the rest of the nodes in the cluster, we try to drive requests to the hot nodes until this node becoming hotter and hotter. And once the temperature is about equal, it will get even amount of requests. So this is something that we are able to do in the database itself, and you cannot do it with external cache, or it's harder to do.
Okay, cool. All right, so I'm going to give just another minute or so to see if we have any other questions come in. Here we go. All right, so can cache be reconstructed from cold start from data written to disk? So the answer is yes and no, but in theory it can, and some databases do that. In Scylla, we do not do that. And we mitigate the same problem in another mechanism that I just mentioned, which is the heat-weighted load balancing. All right. Excellent. So it looks like we've hit a fair number of questions and we are right around time. So I wanted to thank everybody for joining the webinar today. And if you're interested in a follow-up, that's an awesome item right there. I like the monster guy. Right, so if anybody's interested in the slides, you'll get a copy of them. If you're interested in a monster stuffed animal, which I kind of am because that looks cool, drop a note to your friends over at Scylla. Thank you very much, everybody.
Thank you, Eric. And do ping me for Monster.
All right, see you later.
Bye.